So this section, basically we're gonna take a look at the physical properties of ketone aldehyde, and also we can put compare the physical properties with the some class of compounds we already learned earlier, like alkenes and alcohols. So when we say physical properties, we often look at the boiling point and the water solubility. So the boiling point is directly related to and only related to intermolecular interaction of the kind of molecule we are working with, nothing else. So when we talk about boiling point of aldehydes, so we are only looking at intermolecular interaction among aldehyde molecules. If we look at the boiling point of the ketones, again we look at intermolecular interaction among ketone molecules. If you look at let's say aldehyde, okay, and a structurally comparable hydrocarbon. So we use alkene as the example because alkene has CC double bond, which is kind of structurally similar to the CO double bond. Why are we using this alkene? Because if you compare the boiling point of intermolecular interaction, we know boiling point of intermolecular interaction depends on molecular weight. So you have to compare on a very similar molecular weight base. We cannot make sure they're exactly the same, but as similar as possible. So obviously, these two guys' molecular weight is pretty close, maybe 2 unit difference. Okay, and then what you can see, the aldehyde has a much higher boiling point. That is expected because hydrocarbons, you mainly have the induced dipole interaction. But in aldehyde or ketone, because of carbonyl group being highly polar, so entire molecule has appreciable dipole moment. So for aldehydes and the ketones, in addition to induced dipole interaction, you also have a permanent dipole interaction. And the permanent dipole interaction usually is somewhat appreciable and sizably stronger than induced dipole interaction. Not dramatically stronger, but sizably stronger. So that leads to the boiling point is about like 50 degrees higher. Okay, and obviously although it's ketone aldehydes are polar, but it does not have those highly polar, the XH bonds like OH bonds, NH bonds. Okay, so ketones aldehydes that they can really engage in strong hydrogen bond, intermolecular hydrogen bond, because hydrogen bond you need a hydrogen bond acceptor and a hydrogen bond donor. A hydrogen bond donor often is a OH bond, okay, NH bond, okay. Those two kind of XH bond, okay, they are typical hydrogen bond donors because those, the XH bond has appreciable, the dipole moment, okay. So that can give you relatively strong hydrogen bond. But the ketone aldehyde, you have neither OH nor NH bond. So it cannot form hydrogen bond by itself. So its boiling point, it's also appreciably lower than the alcohols with similar molecular weight, because the alcohols, as we know, have both hydrogen bond donor and hydrogen bond acceptor. Okay, but when it comes to solubility in water, we know hydrocarbons are insoluble, and the ketone and aldehyde, they have appreciable solubility. Why? Because why the ketones aldehyde, they don't have hydrogen bond donors, but they do have hydrogen bond acceptors. The carbonyl oxygen can accept the hydrogen bond. And the water, they do have hydrogen bond donors. So yes, they can form hydrogen bond. Okay, they can form hydrogen bond with you know, the aldehyde or ketone. So aldehyde and ketone, they have a much higher water solubility than hydrocarbons. Okay. Any questions about the intermolecular interaction of physical properties? The source of aldehydes and the ketones. Some of aldehydes and the ketones, they are nature occurring. Here are some examples. And then in early part, especially organic one, we already learned quite a few reactions can give us aldehydes and the ketones. And in as early as in chapter 8, we already learned that ozonolysis can give us ketones or aldehydes, depending on the structure of the alkene. And also, in chapter 9 in organic 1, we also learned that the hydration of alkyne can give us ketones mostly, and in some cases can give us aldehyde. Okay. And in chapter 13 of organic 2, we learned the Friedel-Crafts oscillation can give us ketones. And then in chapter 16, we have learned that if we take a primary alcohol, we can use PCC or PDC to oxidize into aldehyde. This oxidation, we have to carefully avoid water. So if we want to get the aldehyde. And if we have a secondary aldehyde, we can oxidize and use any condition pretty much. Then we can get the ketone. Those are older reactions we have learned. And then what about, if we have a carboxylic acid, can we get aldehyde? Okay, convert a carboxyl group to aldehyde? And this is actually in the exam too. Okay, you have seen it. Okay, and I'm pretty happy to see many of you got it because this can be figured out using logical manner because we know we haven't learned a single reaction to do this. Okay, but we know this one we can, if we want to get aldehyde, we could. If we have primary alcohol, we can get the aldehyde, okay, by PCC or PDC, okay, and we know that we could convert, the carboxylic acid to primary alcohol. So then, the put the two steps together, we can accomplish this conversion. Okay, so first one, carboxylic acid to alcohol, only one method, no others. No others, only one method, lithium aluminum hydride. First treat with lithium aluminum hydride in THF diethyl ether, then using water to work up the mixture, you get a primary alcohol. Then using PDC or PCC in dichromethane, it will work. Here's a real world example. You can do the two-step reaction, convert the benzoic acid to benzaldehyde. And then the next question is if we have a aldehyde, can we convert to a ketone? Okay? So obviously we need to add a fragment with R prime. Okay, that's needed because we don't have it in the starting compound. Okay, so how do we do that? Okay, again, there's no single step can do it. We haven't learned that. Okay, but we know that from chapter 16, if we do Richard synthetic analysis, we know if we have a secondary alcohol. Okay, then we can oxidize the secondary alcohol. We can get a ketone. Then can we get the secondary alcohol from this aldehyde? Yes, we can do that. We learned in chapter 15. Okay, so we just need something organolithium and the THF. That's the first step. Okay, then you had acid. You will get that. Okay, so that's basically, the how you're gonna do the this kind of conversions. So this is chapter 15 content. This chapter 16 content. Okay. So here's a real world example. So if you have this aldehyde, if you want to add a butyl group and then convert to ketone, so you can add a butyl magnesium chloride or bromide in THF or diester ether. Then you acidify it, you get a secondary alcohol, we treat it with chromic acid, you get this ketone product. So those are just some exercise based on the knowledge we learned from early chapters. Okay, so now we're gonna learn some new reactions. Okay, so we're gonna look at the reactions of aldehydes and the ketones. Okay? So actually we already learned quite a few reactions of aldehyde and ketones, like Wolff-Kishner or Clemmensen reduction. This is two reactions that we can reduce carbonyl group to CH2s. And those two reactions, because of their mechanisms, are not, the involved in the later reaction, so we didn't talk about it. But we did learn that the two reactions, maybe three reactions in chapter 16 where the carbonyl group can be reduced to CH2s. Those are the, the not CH2, carbonyl group reduced to alcohols. They're basically catalytic hydrogenation, sodium boron hydride, and the lithium aluminum hydride. And we did spend some time looking into mechanisms of the sodium boron hydride or lithium aluminum hydride reduction. And and also in chapter 15, we have seen that Grignard reagent or organolithium can undergo nucleophilic addition to the carbonyl carbon. So actually, both the metal hydride reduction and organolithium, organomagnesium nucleophilic addition, they both these types can be treated as nucleophilic addition to carbonyl groups. Okay, we already have seen, the a number of times. Okay, like let me just let you just refresh what you seen for the chapter 15. If in chapter 15, okay, we can treat organolithium or Grignard as a carbon anion, then this is considered the rate limiting step. So that is nucleophilic attack to carbonyl. And metal hydride reduction, let's say BHH minus, okay, is kind of the same. Again, that is nucleophilic addition, BH3. Okay. Again, that's nucleophilic addition. So this type of reaction we can generalize into So the this is a kind of reaction you will be seeing, okay, probably over 100 times, okay, in the throughout the semester, okay. So the you have nucleophile, it will attack electrophilic carbon, then the pi bond of the pi component of the CO double bond breaks, give you a oxide ion. So this step you're probably gonna see 100 times, okay, in the organic. So you already have seen probably like 15 times already. So it's the 80, 90 times to go. Okay. And that so this process often is a relative endothermic process. The reason being is that CO double bond is a fairly strong bond, So the breaking it often costs energy, So that in many reactions involve this step often is the rate limiting one. Okay? Often is rate limiting one. And we will examine this kind of the reactions in the in a formal manner throughout this thoroughly throughout this chapter. So often in real reaction you often have the reagent. You often have a nucleophilic fragment. The reagent you use, you have nucleophilic fragment, the nucleophile, and the electrophilic fragment. That's one without that pair of electrons. So the net effect, this is not a mechanistic. This is not a mechanism. It's not a reaction. Is the nucleophilic fragment with a pair of electrons add to the carbonyl carbon, and that the electrophilic fragment add to the carbonyl oxygen. So that's the kind of reaction pattern we'll be seeing in this chapter. So and we will be looking at the both the thermodynamic the aspect and the kinetic aspect of those type of reactions using hydration as the first the example. So hydration, as the name suggested, okay, is a ketone or aldehyde react with water, okay, and then the water will be added across the CO double bond. So what happens is water is H2O. So HO is the nucleophilic fragment. Okay. So HO will add to the carbonyl oxygen. Okay. And then if the water has two fragments, obviously you have H, okay, and the OH. So the why this fragment, the nucleophilic fragment, okay, added to the carbonyl oxygen. So the electrophilic fragment, the proton, will add to nucleophilic fragment add to carbonyl carbon, as we see here. Then the electrophilic fragment, the proton, add to the carbonyl oxygen. So usually this reaction is relatively fast. Okay, so often is considered as an equilibrium process, and the product, okay, is called germinodiol because of the product has two OH group connect to the same carbon. That's how the term germinal come from, called germinodiol. You have two OH group and two OH group connect to the same carbon called germinodiol, also called hydrate. Okay, so this reaction we can look at this reaction, from its thermodynamic aspect, means how likely this reaction will be happening, which is quantified by the equilibrium constant, hydration constant, okay? And also we're going to look at the kinetic aspect, with how fast the reaction will be happening, okay? So when we look at the thermodynamic aspect, basically it pretty much boils down to if you look at the if you are given a say acetone solution in water, okay, is it mostly acetone is acetone mostly existing in acetone form, or the acetone mostly existing in the the geminal diol form, okay? So and then if you want to see that, we can look at the the what called the hydration equilibrium constant, which also you can look at this, also can calculate what is the percent of the of the what call hydrate at the equilibrium. Okay, so what you can see is the if here are the structure of carbonyl compounds. Okay, here is structure of a hydrate, and the third column is equilibrium constant, and the fourth column is percent of the the hydrate. Okay, and the at the equilibrium, and the last column is the kinetic aspect. The rate of hydration, relative rate of hydration. Okay? So what you can see is it's a clear trend of equilibrium constant, and the rate is parallel with the trend of the equilibrium constant. So it appears that the going from the formaldehyde to regular aldehyde, you see a substantial, not a substantial, dramatic reduction of hydration equilibrium constant. Dramatic. Okay? And then if you look at the two aldehydes, okay, these two aldehydes, they actually have a very large difference in sterical hindrance. Okay, very large difference because of this aldehyde has a methyl group connect to the carbon. I'm sorry, it has a has a methyl group connect to the carbonyl carbon, and this aldehyde has a tertiary butyl group connect to a carbonyl carbon. As you know, the steric hindrance of the tertiary butyl group is so much larger than the methyl group. Okay, but its impact on equilibrium constant, okay, is only 5 times, not a lot. Okay, keep in mind from here, go from hydrogen to methyl group, equilibrium constant reduced by more than 2,000 times. Okay, but here only 5 times. Okay, now if we compare this one and this one, okay, this one and this one. So what's difference here is the this one, in this case, you have one methyl group connect to carbonyl group. Here, you have two methyl group connect to carbonyl group. So one methyl difference. Okay. So and that actually has a huge difference in equilibrium constant, 700 times lower equilibrium constant. Okay. So what you can see here is the ketone, okay, have a much smaller equilibrium constant than aldehyde. Okay. And it cannot be purely explained by steric hindrance. Steric hindrance did play some role here. If this can be seen by the equilibrium constant difference of these two guys, because of this guy has a much larger steric hindrance than this one. So the steric hindrance, the equilibrium constant indeed is a bit smaller. Okay, is smaller, but the difference between ketone and aldehyde is more important. So basically, what you can see is when you look at how the substitution pattern impact the equilibrium constant. Okay, what you see is the number of LQ groups on the carbonyl group plays the biggest role. Okay, this is 0 LQ group on carbonyl. Okay, these two are 1 LQ group on carbonyl, right? 1 LQ group. Okay, and this one is 2. So 0 to 1, you see somewhere from 2,000 to 10,000 difference in equilibrium constant. Okay, but for between the two aldehydes, the difference only 5 times. not a large difference. Okay, but between 1 and 2 alkyl groups, ketone and aldehyde, again you see close to 1,000 times difference. Okay, so it appears that the number of alkyl groups on carbonyl carbon is the most important factor. Do you agree, no? Because 0, 1, 2, you see huge difference. Pretty much 0 to 1, you see 3 orders of magnitude difference. Okay, now 1 to 2, you see another 3 orders of magnitude difference. So the number of alkyl groups is the primary factor that impact the the equilibrium constant. How do we explain that? Okay. So the reason is when you look at this equilibrium constant, okay, this equilibrium constant is really decided by relative stability of the reactant and the relative stability of the product. So the one reactant is water, you cannot change it, right? So only thing is basically you're comparing, how when I change the substitution pattern, how does it impact stability of this one, and how does that impact stability of this one? Okay? So the biggest difference, okay, can be explained by when you have more alkyl groups on carbonyl group, the carbonyl group can be better stabilized. That causes the primary difference in stability. Keep in mind that if you recall this one, you see the stability difference of ketone and aldehyde. It's 33 kilojoule per mole, right? These two isomers, 33 kilojoule per mole. So if we look at if we take this one just as a hint, okay? Now if we compare just the carbonyl stability, so if we say this carbonyl, okay? Assume we have just can isolate the carbonyl group and measure their stability. Okay, relatively, okay, we isolate the carbonyl group, okay, those 3 carbonyl, okay, and if we treat, say relatively speaking, we treat this one, okay, this one potential energy as 0 kilojoule per mole, okay, oh, okay, yeah, okay, let's see, add this one, okay. Okay, so if this one as reference 0 kilojoule per mole, okay, then aldehyde probably, let's say 33 kilojoule per mole higher, okay, because one alkyl group we know roughly generate 33 kilojoule per mole stability in carbonyl group, right? And then the bottom one will be minus 33 kilojoule per mole, right? Because of the one alkyl group increased stability by carbonyl by 33 kilojoule roughly, okay? So then you will see the stability difference of the ketone and the formaldehyde is like 66 kilojoule. It's a very large difference, okay? So then if you look at here, and then then you can explain why formaldehyde, okay, has the highest, the hydration equilibrium constant, because formaldehyde out of all those carbonyl has the least stable carbonyl, least. If you compare relative, just ballpark number, formaldehyde carbonyl will be roughly 60 something kilojoule per mole less stable than different 60 something kilojoule. That's a lot, okay. And then this one is about 33 kilojoule per mole less stable than this, okay. So that's why you see the number of alkyl groups makes the biggest difference in equilibrium constant, and the rate goes the same way, okay. And then why these two guys still see somewhat difference in equilibrium constant? That is because of in the hydrate, okay, the carbon is 3 hybridides. Now you have 4 groups around it, right? 4 groups around the carbon. So the bigger the LQ groups are here, the hydrate, okay, will experience larger steric hindrance. Okay, but that's a secondary effect. That's a secondary effect. Okay. So the rate and the equilibrium constant go similar manner. Okay. So now if I let's do a few exercise. If you want to see, let's say I have an alkene isomer, let's say C6. Do I have 6 carbons? Yes. C6 carbonyl compound isomers. Okay. If I can write a few C6, you know, the 1, 2, 3. C6, you know, the carbonyl compound isomers. Okay, so if you want to look at the hydration equilibrium constant, which of those guys have the highest hydration equilibrium constant? We have 3. Which one have the highest hydration equilibrium constant? The first one, okay, because that's the only aldehyde, only one with a single, you know, the alkyl group, okay. Then which one has the lowest hydration equilibrium constant? Should be the second one, okay, because of the both the second one, B and C, they are ketones, but the B has a bit larger steric hindrance. Okay? It's not a guesswork. It's just, you know, electronic effect B and C are the same, but the steric effect B is a bit you know, larger steric effect. So B has the smallest hydration. So I'm gonna, you know, I'm gonna class end here. I'm gonna see you guys in the next class.